Hello, everyone. My name is Nicole Jackson, and this is my presentation for the Undergraduate Research Symposium. I'd first like to start off by saying thank you so much for this amazing opportunity to present. And I would also like to thank my mentors, both Professor Laura Jonti and Juliet Wright, for helping me with this research. So, for the title, I have the Muon Collider, analyzing simulated background and signal processes to advance particle tracking. Within this presentation, I'll be going over introducing the muon collider and a significant problem it poses, the objective, methodology, interpretation, results, and conclusion that came from this research. I also have some figures sprinkled in relating to the research that I've done, and I also have a significant figure that relates to what the potential design of a muon collider would look like. So, to introduce the muon collider in its new development, I would like to first previously explain the previous particles that were used in previous particle accelerators. So, particles that have been used have been electrons, protons, and heavy ions. Each of these particles have been used in particle accelerators to advance particle physics and have many new breakthroughs within high energy physics. Now, the muon collider poses many new opportunities that could come from using muons instead of electrons, protons, or heavy ions. The properties of muons that compared to other particles are representative of what makes muons so special. Muons are heavier fundamental particles in comparison to electrons, and they aren't made up of composite particles like protons. Furthermore, compared to electrons, muons have greater mass significantly reduces synchrotron radiation, which is an electromagnetic radiation emitted when a charged particle moves along a curved path. Therefore, unlike protons and electrons, muons have the opportunity to have higher energy and cleaner collision events with the muon collider. However, muons do pose a significant challenge when it comes to the fact that they decay. Muon decay leads to many particles that are decay products of the muon that make up the beam-induced background. So because muons are unstable and decay into particles that make up the beam-induced background, this leads us to our objective. The objective here is because muons decay into particles that contribute to beam-induced background, it's really important to focus on the detector design. What we want to focus on detector design to effectively distinguish between signal and background events in the vertex detector. The vertex detector is the innermost layer of the detector and is responsible for measuring the positions and angles of particle track near the collision point. So, by optimizing the performance of the vertex detector, we can more accurately analyze a particle's track and determine its position along its path. We desire to initially define which of the particles of the beam-induced background resembles the signal the most. So, by using simulations of 10 GeV muon collisions, we can define both signal and the background, and we can identify effective methods to reduce beam-induced background interference and improve particle tracking accuracy. So, I first have figure one here of a schematic layout of the muon collider. Within this box here, there are key processes that occur. One of them is that there's production of high intensity proton beams. These protons are then collided into a target material to produce pions, which then decay to muons. Muons are then cooled using an ionization cooling technique, which then makes the muon beams stable and focused for collision. So these beams are then put into this accelerator ring to then increase the energy of the muons up to about 10 TeV, which then, before collision, right here is where the collision occurs, the particles are then moved into this ring and then they collide, and the detectors are used to analyze the collision events. Now, for the methodology within my research, I have that the initial steps of determining which particles appear like signal we've generated and selected samples based on peak energy distributions of different particle species. We've selected particles that best characterize and sample the beam-induced background that's produced from muon decay. This includes photons at 1 and 10 MeV, electrons at 10 MeV, and neutrons at half MeV. This is then compared to the signal events of the 10 GeV electrons and 10 GeV muons. Thus, by using simulations, we've measured their components of their energy deposition, which is shown on the left in figure 2, and time of arrival for cluster hits in the vertex detector for each particle type. Both figures 2 and 3 relate to the 10 GeV muon. That on the left is the 10 GeV muon's digitized energy deposited, and on the right is the 10 GeV muon's digitized time of arrival. Each of these are validated by energy and time distributions that match our expectations using underlying physics and underlying computational factors. Therefore, to deepen our comparison, we've generated individual normalized plots for the beam-induced background particles as shown in figure 4 and 5, which I'll show in a few seconds. So, moving on to our interpretation, I want to explain what figures 2 and 3 mean with respect to the signal and the other particles that are then compared to that signal. So, in figures 2 and 3, it's representative of the 10 GeV muon signal. Uh, the muon signal is a minimum ionizing particle. A minimum ionizing particle, or a MIP, is a charged particle that loses energy at the minimum rate while passing through matter, such as the silicon in the detector. So, particles with an energy above 1 GeV, including both the 10 GeV muon and the 10 GeV electron signals, are minimum ionizing particles. All energy distribution plots display the energy deposited across the 8 layers of the vertex barrel with center thickness of 50 microns. Therefore, the signal plots are then compared to every other plot that is produced from the other particles, including the 10 MeV electron, the 10 MeV photon, the 1 MeV photon, and the half MeV neutron. So, in contrast to the electron and muon particles, the neutral particles, such as the neutrons and photons, it is understood that they're electrically neutral, which means that they do not ionize and will interact with the detector differently. So all the time distribution plots show the number of entries versus the time arrival in nanoseconds for each particle, which will be shown in figure 5, and which is also shown in figure 3. So in figure 4 here, I want to express some key ideas that I've noticed. So in purple, we have the 1 MeV photon. In pink, we have the 10 GeV muon. In green, we have the 10 MeV electron. And in orange, we have the 10 MeV photon. And lastly, we have the 10 GeV electron, which is also a signal in blue. So some key things that are found in figure 4 of the normalized plot for digitized energy deposited of all samples is that the 10 GeV particles of the muons and electrons have identical peaks at about 0.014 times 10 to the negative 3 GeV. Additionally, a second idea is that the 10 MeV electrons show fewer hits due to their slower momentum. And as you can also notice, they do have a longer distribution than the GeV samples. The last thing I've noticed within this key plot is that photons have fewer hits since they are unable to ionize and their energy distribution looks similar to signal. I would like to also emphasize that neutron samples weren't included in this because they do not have comparable plots to the other particles due to their inability to ionize and how they interact with the detector. Similarly, so the normalized digitized time of arrival is shown here, where it shows all of the samples in a normalized plot. The 1 MeV photon is in purple, the 10 GeV muon is in pink, the 10 MeV electron being green, and the 10 MeV photon in orange, and lastly, the 10 GeV electron in blue. So some key things I found from this plot is that the 10 MeV electrons arrive to the detector much slower than that of the 10 GeV particles and the 1 MeV photon. This is because the 10 MeV electrons move at a speed slower than the speed of light in comparison to the other particles. Additionally, I've noticed that the photons have the inability to ionize, as we know, and so this causes their differences in their plots, as you can tell by the 1 MeV photon and the 10 MeV photon. And so lastly, I would like to also emphasize that the 10 GeV muon and the 10 GeV electron have highly identical plots or very similar plots due to them both being minimum ionizing particles. So, so some of the results that came from these plots and from other research aspects are that the 10 GeV muons and electrons produce closely related plots. This is because both behave as minimum ionizing particles, which is to be expected. Additionally, the peaks and troughs in the time of arrival plots for the 10 GeV muon and electron plots correspond to their arrival at each of the 8 layers in the vertex barrel. The 10 MeV electrons exhibit a broader energy loss distribution and produce fewer hits due to their low momentum. Also, although photons produce fewer hits due to their inability to ionize, Their normalized plots resemble those of the 10 GeV signal particles, including both the muon and the electron, more closely than any other particle type that was exhibited, including the 10 MeV electron and the 1 MeV, or the 1 MeV photon did represent it, sorry, just the 10 MeV electron and the half MeV neutron as the background particles. Lastly, neutrons were excluded from the overlay plots because they arrived at the detector much later and produced significantly fewer hits due to their inability to ionize. So this gives us this preliminary conclusion that we've determined that photons will be the most problematic beam-induced background particles, and as they produce plots that resemble the signal the most. Therefore, ongoing efforts aim to reduce the background interference due to these photons and enhance signal detection and further work by adjusting the sensor thickness within the detector. We're also looking into different strategies to reduce the amount of beam-induced background interference due to the background particles. So I'm excited to be able to share this research, and I appreciate all of you guys listening. And I hope you got good information from this presentation. So thank you so much for watching and listening.